everyone, we are Team Helios, and in this presentation we'll briefly explain our 3 ideas. Our first idea, which we hope to pursue in the NASA Big Idea competition, involves heating a magnetic heat transfer fluid with the heliostat and using its magnetic properties to increase the heat transfer coefficient. Our next idea is a blast furnace that is suitable for the lunar environment, and our final idea involves using the magnetic caloric effect to cool molten metal.
We identified these 4 major difficulties for metal manufacturing on the lunar surface. Therefore, we decided to leverage renewable energy to tackle one of the 4 major steps of metal processing in order to use lunar materials to create metal products.
Our main concept and focus is a magnetic heat transfer fluid, which can be used to power thermal processes such as smelting for a blast furnace or other manufacturing processes that require heat.
Our idea is based on a heliostat system, as there are currently lunar deployable solutions that have been developed. They are great for heat-intensive metal processes and have a really high power generation capacity. However, there are currently obstacles including inadequate energy transfer, as well as the microgravity and thin atmosphere environment.
On the right is our proposed system. Rather than generate electricity, we want to concentrate and redistribute thermal energy to separate ilmenite. To accomplish this, we are using a metallic working fluid and passing the heated metallic fluid through a heat exchanger. The heat exchanger will heat hydrogen gas up to 12,000 degrees Celsius. This gas can then be used to heat and separate ilmenite by induced convection. The innovative part of this design is the use of a magnetic fluid at a high operating temperature and in this type of application on a large scale. Ferrofluids are fluids attracted by magnets and have special heat transfer properties. The heat transfer coefficient, which is important in convection, can be manipulated by introducing a magnetic field. This means we can increase the heat transfer coefficient in order to easily heat regulate to at least 1,000 degrees Celsius. However, this principle and all of these properties are typically tested and used on a small scale. Additionally, NASA is researching the use of electromagnetic fields to move ferrofluids. This means that the cold magnetic fluid could be moved up the heliostat without using a pump and thus would save more energy. Our main model will be an energy model that tracks the net energy and energy loss throughout the entire system. From this model, we will determine the heat transfer coefficient and how much exposed pipe will be needed at the receiver to ensure proper thermal energy at the heat exchanger. This will be tested for multiple heat transfer liquids and for multiple strengths of magnetic fields. There will be assumptions about the heliostat design parameters and estimates for the irradiance on the moon. Additionally, we are working on flow and pressure models to ensure the fluids will move properly around the pipe. Finally, we will have to account for the reduction in magnetism that occurs once ferrofluids reach a certain temperature, known as the Curie temperature. We expect to still see an increase in the heat transfer coefficient, but not as much as we would see at lower temperatures. So far, we have verified that the energy at the receiver can raise the working fluid temperature to above 1,000 degrees Celsius. This is supported by the fact that heliostats on Earth operate at a higher working temperature and that the moon has more direct irradiance than the Earth due to its lack of atmosphere. But we also created an analytical model that accounts for the insolation at the south pole of the moon and the mirror area of the heliostats to calculate energy produced by the heliostat field and the operating temperature. Additionally, we proved that there's sufficient flow of magnetic fluids within a magnetic field. As long as the heat transfer fluid is not an isotropic mixture, the metallic particles will not become pinned against the pipes. Most importantly, we found ferrofluids that can reach the required temperature without losing their metallic or heat transfer properties. Previously, we were concerned that these ferrofluids would become paramagnetic at their Curie temperature and lose their heat transfer properties. However, the magnetic spin of paramagnetic fluids will realign when a magnetic field is present, so there are still improved heat transfer properties. This is an experiment we are planning to perform in January before the NASA Big Idea proposal deadline. The magnetic fluid is heated and pumped through an electromagnetic field, and the heat transfer coefficient is measured. From this experiment, we'll be able to show how both the temperature and the magnetic flux affect the heat transfer coefficient. If we continue this research, we will likely repeat this experiment with various ferrofluids and at hotter temperatures.
Our second idea is a lunar blast furnace. Ilmenite is an ISRU material of interest from NASA for iron and oxygen production. The idea of a blast furnace itself is trivial. However, adapting the system to be self-contained by recycling catalysts and separating byproducts is novel and highly innovative. The lunar blast furnace can be separated into 5 subsystems. Each can be proved feasible while isolated, and proof of concept and experimentation is needed to integrate into one solution. The first subsystem is extracting hydrogen gas and carbon monoxide from lunar regolith. The reduction of ilmenite can be done with both hydrogen gas and carbon monoxide. These gases can be attained by heating lunar regolith and separating using a series of membranes. The temperature range of 300 to 600 degrees Celsius releases hydrogen gas, and 700 to 1200 degrees Celsius releases carbon monoxide under a vacuum. This is an example of an experimental setup for extracting volatiles from lunar regolith. From the reaction, we may have H2O, oxygen, hydrogen, and carbon monoxide gases. These can be separated with a series of membranes, and the hydrogen and carbon monoxide can be recycled catalysts, and the H2O and oxygen are beneficial byproducts. The next subsystem is furnace smelting and the reaction. We have all the resources necessary to perform the chemical reduction of ilmenite. However, without an atmosphere, we need to control the pressure and temperature within the blast furnace to prevent vaporization of the metal. The next subsystem is separating the slag and pure metal. It is more difficult to separate the metals by density under lunar gravity, so we can cool the metal, grind it into a powder, and use magnetic separation where the iron is magnetic. This raw iron can be used for manufacturing. The final subsystem is reheating hydrogen and carbon monoxide gases. This takes in the recycled and extracted gases from the furnace in regolith, stores them, and reheats to be used in the blast furnace again. In this application, the gases need to be heated to at least 1050 degrees Celsius in order to smelt the ilmenite. Calculations for this proof of concept include the mass of gas needed given ilmenite ore being smelted, given the chemical equations, and the mass of regolith needed to extract the mass of gases. Additionally, we need the energy needed to heat the gases and energy to smelt the mass of ilmenite. Also, we will have heat loss from the gas in the pipes, given the length of pipes. Finally, we'll need the energy needed to pump the gas around the system and through the membranes.
Magnetic cooling utilizes the phenomena linked to the magnetic Couric effect, which causes certain materials to warm up when the magnetic field is applied, and returns to its original state upon removal. However, the material radiates away its heat during the magnetized states, leading to the material achieving lower temperatures compared to the original state. The following showcases a basic model of a magnetic cooling, where the motor derives the magnet to achieve differing states, while the magnetic Couric material achieves the ever-decreasing lower temperature. The following proof of concept relating to magnetic cooling combines the ideal phenomenon of the cryogenic treatment of metals combined with the magnetic Couric effect to develop a design that cures the metal at low temperatures with relatively reduced energy loss compared to liquid nitrogen treatment and compression-based cooling system to provide uniform flow, minimum energy loss, and a cryogenic treatment for metal cooling, which enhances the microstructural properties. The following analytical calculations are used to evaluate the magnetic Couric effect based on the magnetic entropy change as well as the specific heat capacity. As you can see by both of the graphs derived from the equations listed, there's a significant drop-off in both values at the 600 Kelvin mark. This could be deduced from observation analysis as the cure point. This is exactly the reason why this proof of concept or idea could be deemed as too innovative and experimental for the purposes of the Big Idea Challenge.
Moving forward, we will continue working on the analytical models and create a budget for experimentation. We will then cross-reference equipment at Georgia Tech for experimenting with for the NASA Big Ideas proposal. Additionally, we will create CAD models. Thank you for listening to our presentation.